So now let's talk about some alkyne reactions that are similar to alkene reactions. First of all, catalytic hydrogenation. So we saw in the previous units that if you have a pi bond, react it with hydrogen in the presence of a metal catalyst, you'll get alkanes. Same thing happens with alkynes. So let's imagine then we have our alkyne. Could be R could be hydrogen, or R could be any other carbon group. Hydrogen in the presence of platinum or palladium or platinum or nickel, probably whatever's cheaper or whatever gives you what you need. There you have it. So the two pi bonds of the alkyne get reduced to alkanes. So you start as an alkyne, you go to the alkene, and you go to the alkane. And you can't stop it. It just goes all the way to the end. So in this particular action, you go from alkyne to alkane without stopping. You can't trap the intermediate alkene because the reaction just happens too fast. So what happens though if you want the intermediate alkane? You don't want the alkyne, you want the alkene. Well, to do that, you have to use something called Lindlar's catalyst. Now, Lindlar's catalyst is, well, let me just draw the reaction. Let me give it a lot of space over the arrow because it's a big soup. You have to have hydrogen. And now you're going to have palladium on barium sulfate in the presence of something called quinoline. And methanol. And that will give you the cis alkyne. The cis alkyne. Now, this is Lindlar's catalyst right here. Everything you see here except for the hydrogen is Lindlar's catalyst. You add the hydrogen to Lindlar's catalyst. So hydrogen in the presence of Lindlar's catalyst will give you the alkene. Now what's happening here is you have what's called a poisoned catalyst. It just means that there's less active sites to work with in the catalytic palladium. So it slows the reaction down, and it makes it possible to capture the alkene before it reacts to the alkyne. In fact, it slows it down quite a bit. So it's very simple now to capture the alkene and stop it from going all the way to the alkane. And you get the cis alkene. But you know what I'm going to say, right? Well, how do you make the trans alkene? Because chemists always do that. If I can go from the alkyne to the alkane, well, how do I get the alkene? Well, here's how you get the cis alkene. Well, now how do I get the trans alkene? What if I want the other one? So you have to have lots of, tools in the drawer to do chemical synthesis. So you have to have different ways of doing. You have to have procedures to do different things. So now we can make we can go from the alkyne to the alkane. We can go from the alkyne to the alkene, but only cis. Now we can go to trans using this method, reduction of alkynes with liquid metal ammonia. So let's just see the general reaction. Sodium metal and liquefied ammonia. So the sodium here is sodium metal. So it's not the cation, it's the actual metal with the one valence electron. And the NH3 ammonia is liquefied. So it's very cold. You cool this reaction way down, and you'll get, get a little more space here. You'll get, instead of the cis alkene, you'll get the trans alkene. And that's how this reaction is going to work. Now, what's going on in the flask? Well, first thing you have to know is that when sodium metal is dissolved into ammonia, And remember, this is liquefied ammonia, so it's going to be quite cold in the flask. To liquefy ammonia, you got to cool it down quite a bit. You're going to get, now what's happening in the flask when sodium metal is added to liquefied ammonia, so it's really cold in there, you'll get what's called a solvated electron. Plus sodium cation. So we call this a solvated electron, and it is a deep blue color. You'll know you're successful in creating the solvated electron because of the color of the solution. Liquefied ammonia is clear and colorless. Sodium is a shiny gray metal. When it's fresh, it's shiny gray. It oxidizes quickly. You throw them in the flask together at negative 78 or whatever, and you'll get a nice, beautiful blue solution. And that's how you know you've created this solvated electron. Okay? So now, the mechanism of this reaction is as follows. First thing you do, you liquefy the ammonia. Second thing you do, you throw in the sodium, form the solvated electron. Then you add your alkyne. So now we have our alkyne. And we draw the electron. Now it's one electron, right? So we have to do single electron transfer. So this fishhook arrow will attack one of the carbons of the alkyne, and the pi bond will break, going to the other carbon. Now, this is coming in from a backside attack. So it attacks the backside of one of the p orbitals, forcing the electrons to go in the other direction to the other carbon. So we have electrons here and now here. So you can already see the electrons are already in a trans configuration. So now we have what's called a radical anion. A radical anion. And we've already seen in this unit that anions on sp2 carbons are very basic. Anions on sp2 carbons are very basic. In fact, they're so basic, they will deprotonate ammonia. Okay, so we're getting the anion here attacking the hydrogen of ammonia, or a proton of ammonia. And that will give us the protonated version of the radical. So now we just have a free radical. Instead of a radical anion, we have a free radical. Okay, so now next step, another electron, another solvated electron, will add to the orbital, to the sp2 orbital, where the single electron is, where the radical is housed. It'll add to it. And now we have an anion, which we've already seen. These things are basic enough to deprotonate ammonia. There we have it. Now that will generate our product, our trans alkene. And that's the mechanism of this reaction. Now, keep this reaction in mind, especially if you're going into organic 2, because there's another reaction there that's very similar called a Birch reduction, where you can reduce an aromatic ring. But for now, we're going to leave it here. We're not going to talk about Birch reductions in this class. Just keep it in mind. If you're going into organic 2, you're going to see a similar reaction later on.